Okay, so just for everyone's information, our remote teaching has been extended to week 4. So we will continue doing this and until the week 4 at least. And then for the recordings, both the lectures and the discussion sections were posted under the same playlist. So the link is available on the CCLE homepage. You can check it there. All right, so do we have any questions about the materials we covered last week before we continue with the new material? All right, so if there are no questions, I'll just continue. So last week, the most important concept we cover is the moment generating function. Just as a very quick review, when we say moment generating function, and we are talking about a moment generating function of a real value random variable x. So it's scalar valued. And the function itself has argument t. So t is also a real value. And when we define the moment generating function, we define it as the expectation of some transformation on the random variable x. And this transformation involves t. So it's exponential to the tx, t times x. So therefore, you can see that when we change the t, the function value will change accordingly. But the expectation is about the distribution of random variable x. So that's why when we try to calculate this function, or we want to simplify the form of the function, we will use the probability mass function of x if x is discrete, or the probability density function of x if x is continuous. Then we change this calculation problem to a summation or an integration. So the trick for simplifying this expectation is to use the fact that for a probability mass function, this p probability of x, big X takes value small x, its own sum over all possible values of small x will be equal to 1. And for the probability density function, if we do the integration of the function, it's equal to 1. So we will use those two facts to help us simplify the summation we need to calculate or the integration we need to calculate here. So that's what we did in last week. So in addition to the calculation of moment generating functions for common distributions, including say Poisson, which is a discrete distribution, binomial, another discrete distribution, we also consider two continuous distributions, the exponential distribution and the normal distribution. Okay, so after we did those examples and the calculations per se, we talk about the properties of MGF. We talk about two important properties. One is about the MGF of a linear transformation of a random variable. So let's say we already know the MGF of x, and we just define random variable y as a linear transformation of x. Then we don't need to derive the MGF of y from scratch. We could just apply the MGF of x by this formula. So it gives us this nice transformation. You can carry over the linear transformation to the transformation on the MGF. Okay, so therefore it opens us a lot of flexibility. And we have seen an example about the general normal distribution, right? With any mean mu and any variance sigma. As long as we know the MGF of a standard normal variable, we could use this formula by writing the general normal variable as mu plus sigma times the standard normal variable. And then we could directly use the standard normal MGF to derive the MGF of the general normal random variable. That's the first property about transformation. The second property is about this independent random variable sum. Okay, so what we say is that if you have two independent variables and you know their respective MGFs, then what you can do is that if you are interested in the MGF of the sum, x plus y, you could just multiply the MGF of x with the MGF of y. Then that's the MGF of x plus y. So this is just based on a very important property about the independent variables and the expectation of their product. So basically, we know that here, when we have the MGF of x plus y, we can write this function inside as the product of e to the tx times e to the ty. And then we use the independence property to factorize this expectation of a product as the product of two expectations. And then that's the MGF of x and MGF of y. That's what we did. So with this result, the next important implication is that if we have n IID random variables and we are interested in their sum, then generalizing that result, we can show that the MGF of the sum is the product of their individual MGFs. And because they are identically distributed, right, the second ID, that means they share the same MGF. Then the MGF of the sum is just the power, nth power of the MGF of one individual random variable. So I believe that in the discussion section, our TA Dongyuan has covered the fact that give you the result for the MGF of the average. So the average is basically the sum divided by n. N is the number of random variable here. And that has very important implications later as we started talking about statistics. So far, all the discussion is about probability. So once we apply these probability results to a particular sample, so then you will see later that we will refer to x1 to xn as a random sample so that each xi is the random variable corresponding to one observation in our sample. So in this case, n stands for sample size. And when we take the average of x1 to xn, we call that sample mean. And that sample mean is the most common and the most basic statistic we will talk about. So therefore, the results over here will have very important implications later. All right, so these are my very quick recap of what we have covered in our last week. So today, to start our new materials, so the first one I want to talk about, but I want to say, make it clear that this is optional material. So the next section, next part is optional. I don't really expect that for people who are not very familiar with multivariate calculus to fully understand it as of now, but of course, if you can understand, it's better. But I think this will be a very like a teaser for when we talk about multivariate statistics. Probably you will learn that later in your study. Okay, so this is just to generalize the MGF idea from a univariate distribution. That means we talk about one random variable to a bivariate distribution. That means we talk about a pair of random variables and their joint distribution. Okay, so we call this joint MGF. Okay, so in this setting, we talk about, it's about a pair of random variables, and we denote the pair as x, y. Okay, so again, both x and y are scalar valued, real valued, and here, let's just assume it for simplicity. That is, we have the, sorry, let me just say, yeah. So let's say, given this pair of random variables, and let's just assume for simplicity that they are both discrete or they're both continuous. So I just try to make the notation simpler without talking about the case that one is continuous, one is discrete, but the definition can be similar. Okay, so let's just say that if both x and y are discrete, okay, discrete random variables, then the joint MGF, now the function is a bivariate function itself. So let me just put it here. So the subscript becomes the pair, and the argument is two-dimensional. Now, instead of t, and in addition to t, I have an s. So both s and t are real valued. So it's defined as the expectation of exponential of s times x plus t times y. Okay, so this is the definition. If for some of you who know a little about linear algebra, essentially what we are doing here is, let me just say, S and T being real values, this is no. So in linear algebra, this is actually the result of an inner product of two-dimensional vectors. So essentially, I can write it as ST is a two-dimensional vector inner product with this x, y. Okay, so this is what we did in linear algebra. So basically, you put x and y, this pair, as a two-dimensional random vector, and you do its inner product with a two-dimensional vector of fixed constant, a two-dimensional fixed vector. So this is the product in the linear algebra sense or the vector sense. So previously, see, our definition of the MGF is t times x, right? Because x is one-dimensional, t is one-dimensional. Now we generalize it to two-dimensional, so it becomes their inner product. So the key is that no matter what dimensions your vectors have, their inner product is always a scalar. And that's what we have here. So Sx times Sx plus Ty. Okay, so then, yeah, so this is the definition. If they're both discrete, then maybe I should put this sentence down here. Okay, if they're both discrete, then the expectation will be written as a double sum. So basically, I'll sum over all possible values my random variable x can take, and all possible values my random variable y can take. And then I'll just use the definition of expectation. So it's exponential s to the s times this particular value small x plus t times this particular value small y times the joint probability that x takes small x and y takes small y. Okay, that's the definition. And here, when we talk about the two variable pair here, we need to consider their joint distribution. Okay, so this is the joint distribution whenever these two events happen simultaneously. Okay, this is the discrete case. And I will write the continuous case. Or if x and y are continuous, okay, then we will not write double sum, but a double integral. So in this case, I will do integration of my x, its real value. So I can just write negative infinity to positive infinity, and same for y, okay? And still, e to the small s small x plus t times small y times here, I need a joint density of x and y at small x, small y. And then I do dx, dy. Okay, so here in this definition, where fxy is the joint PDF of x, y, this random variable pair, bivariate random variable. So this is also a very brief introduction to multivariate statistics. So here, if you have a two-dimensional random vector, then the random vector's joint density function will have two arguments. If you have p-dimensional random vector, then the density will have p arguments accordingly. Okay, so this is just the definition. And based on what we have said about the independence, something you could recognize here immediately, right? If you have x and y, if you know beforehand that x and y are independent, then you can actually simplify this form. So if x and y are independent, then you can see this mxy, this joint MGF, by factorizing this exponential, right? Because we know the exponential function can be written as a product e to the sx times e to the ty. We know this. And then by independence, independence will give me expectation of e to the sx times expectation of e to the ty, right? We have this. And now we know by definition of the MGF of x and the MGF of y. It's actually the MGF of x at s times the MGF of y at t. That's it. So this joint MGF can be factorized as the product of marginal MGFs under independence. That's what we want to say. Okay, and what's the use of this MGF? Similar to the univariate MGF, it can give us moments. But here, because it's joint MGF, it can give us joint moments. Okay, so basically, to put it simply, we can say that to obtain joint moments of x and y. Okay, by joint moments, we mean the expectation of, let's say, x to the power r times y to the power v. Okay, so this is just the RV joint moment of x and y. So previously, we just have expectation of x to the power r, and we can have r equal to 1 or 2, right? That's the first moment, second moment. And now we can have their product. So this is called the RV moment of x and y. Okay, and for this, we can show that by Bivariate Taylor expansion. Okay, which I will quickly show you, I think, later in the class today. But for now, I'm just giving you the result. So by the Bivariate Taylor expansion, we can show that this moment can be corresponding to the partial derivatives of this joint MGF by taking the rth derivative against the first argument, v's derivative against the second argument. And with that partial derivative, I evaluate it at 0, 0. That will give me this moment. So recall that we show this result for the univariate MGF by doing what? We do the definition by Taylor expansion on the exponential function inside the expectation. And we do another Taylor expansion on the MGF alone directly. And then we match those two Taylor expansions. And we show that, oh yeah, the first moment of x corresponds to the first derivative of the MGF at 0. We do the Taylor expansion for the MGF around 0, by the way. So that's why we can show that. So here we can show that similarly by doing two-dimensional bivariate Taylor expansion. So anyway, here the result is that this is equal to the partial r plus v of the mxy, okay? And partial r and s, sorry, partial rs times partial vt. Yeah, so I'm going to do the, maybe this is not the right way to write, right? Sorry about notation. I'll just rewrite it. Partial r plus v mxy partial sr partial tv. So I take the derivative against the first argument for r times, and I take the derivative against the second argument t for v times. Yeah. And so this is the function, the partial derivative function with arguments s and t. And I would evaluate this at s equals 0, t equals 0. Okay, so that will give me the corresponding moment of x to the power r, y to the power v. Okay, any questions about this? So later, as I show you how to do the two-dimensional Taylor expansion you should be able to verify this yourself just by following the same strategy we use for verifying the moment result for the univariate MGF. Okay, before we conclude this part, I want to say 3 interesting properties about this joint MGF. These are very obvious based on the definition. So the first property is that if you set the second argument t to be 0, okay, then by definition, you can see that it becomes just expectation of exponential to the sx, okay? And this is just the definition of the MGF of x at s. Okay, so you can reduce this bivariate joint MGF to the marginal MGF of x. Then symmetrically, if I set the first argument as 0 but keeping the second argument as t, then obviously this is the MGF of y at t. You again have the reduction. And furthermore, what if you set the 2 arguments to be equal? Let's just say t and t. Then again, by definition, you can combine the 2 terms in the exponential function. So you can write it as t times x plus y, right? And then by definition, this is the MGF of x plus y at t. So again, you can reduce this joint MGF from a bivariate function to a univariate function because here the 2 arguments are equal to each other, right? So then it doesn't make sense to keep both arguments. You can reduce them to 1. And then you find that this is just the MGF of x plus 1. So these are just some fun math facts based on the definition of the MGF, but I think it's worth mentioning so that you can see better this definition. Okay, so as I said, this joint MGF part is an optional material, but I just want to mention it here so that you can, maybe this can be some basic background for your future learning of multivariate statistics. All right, so the next major topic I will talk about is what we call, let me number the pages, is what we call the delta method. So which is very important even in graduate level statistics class. And let me put it here. So the delta method is a way to do approximation. Okay, so it is an approximation method for calculating expectation and variance. Okay, so the question is, to motivate this delta method, suppose that we know a random variable x has expectation denoted by mu sub x and variance denoted by sigma square sub x. This is what we know. And we know that there is a g function that transforms x to y. So here x is real valued, y is also real valued. So g is some function we know. And the question is how to find the expectation of y after transformation and the variance of y. That's the question we try to address here. So let me just ask you this question first. How would you approach this problem? How would you calculate expectation of y and variance of y if you have more information? So that would be the ideal answer. I will put it here. So the first answer, the ideal answer we would have is to use the definition of expectation of y and variance of y, right? By definition, use the definition right? So basically the expectation of y would be equal to the expectation of g of x, right? That's what we know. And how do we calculate this? By definition, we would know that this will require us to know the distribution of x. If it's a discrete distribution, we will take the sum of at all possible values x may take, right? Do you know this by small x? So it's g small x times the probability x takes value small x, right? If x is discrete. Otherwise, if x is continuous, we will do integration. G of x, fx dx, right? And fx is the density, PDF of my x. PDF of x. Okay, this is what I would do for my ideal solution. But unfortunately, here we don't have the distribution of x known. We just know its expectation and its variance. That's it. And knowing the expectation and variance doesn't mean we know its probability mass function or probability density function. So our information is too limited to carry out this ideal answer. But this is what I say. But P of x equals x and fx, or I should say, or fx is unknown. So basically we say that the distribution of random variable x is only known up to the expectation and the variance. We only know it up to this extent, no, nothing more than that. So that's why we have to do some approximation. Okay, and here the approximate answer is given by the delta method. And the nature is to approximate this g function by Taylor expansion. So we can, when we do Taylor expansion of any function, we are actually using a polynomial of x, polynomial function of x to approximate it, right? And then we can introduce terms including x, x squared in the expectation so that we can just use the mean and variance. That's the basic idea. Okay, let's quickly do it. So basically, you see that using by Taylor expansion, we will approximate g. So this is to approximate g x by a polynomial function of x. This is the basic idea behind Taylor expansion in all cases. And there's a question in the chat box. This is the, no, of course, this is the core material. Only the joint MGF is optional. Now we are back to the delta method. This is what everybody should learn. And as I said, this is also something you will find useful in your graduate study. Okay, so by Taylor expansion, we have y equals gx, okay? And we want to expand it at the mean of x. And you will actually see very quickly why this will be very helpful, right? When we do expansion, usually this expansion should be around some point which is meaningful to us. So here, the meaningful point is the mean of random variable x, which is mu x. And also, this can make us use this knowledge, the expectation that is known. So let's see, what happens if we do expansion around mu x? So first, we will have G at mu x plus the first order term will be x minus mu x times G prime, the first derivative at mu x. And second order, it will be x minus mu x squared divided by 2 times G double prime at mu x, and so on. So I only keep the first two terms in the Taylor expansion, because for the later terms, actually, we don't have the knowledge for higher moments anyway. Okay, so with this, right, now you can see this offers a lot of flexibility for me, because anything inside the G function, like G mu x, G prime mu x, G double prime mu x, they become constants. They are no longer involving the random variable x. So therefore, when I take expectation of y, those constants will be out of my expectation. And what's remaining in my expectation are just the polynomials of x, like x minus mu x squared. These will stay in my expectation. And these are related to the moments of x, which I have knowledge of. So basically what I said is, if I take expectation of y, then based on this expansion, you can see that G mu x will stay out of expectation because there's no random variable. Mu x is the mean, it's not random anymore. Only x is random variable. And second term, you see G prime mu x is a constant. So I get it out of my expectation times expectation of x minus mu x. Okay, that's my second term. And the third term, this G double prime and mu x over 2 will stay out of my expectation. And inside expectation, I have x minus mu x squared, and so on. Okay, so now you see, if I just, here I'm going to say I'm going to do approximation. So for the remaining terms, we know these will involve x cubic, but for x cubic, even if I put it in the expectation, I cannot calculate because I don't have the information. I only have the first moment and the second moment related to the variance from the result, from the knowledge. So therefore, I would drop the remaining terms by changing the equal sign to an approximation sign by only keeping the first 3 terms. Okay, the key is that the second term here is actually equal to 0. The reason is that expectation of x is just equal to mu x. So if I put it here, you can see it's basically this. Okay, so this term, I know it is equal to 0. And for the third term, you know, our knowledge actually can be used. This expectation of x minus mu x squared is actually the definition of variance of x. So this is just sigma x squared. So after all, you see, we find an approximation for the expectation of y just based on mu x and sigma x squared. So let me just write a final form here. So expectation of y, which by definition is the expectation of g of x. Although we cannot do the ideal or exact calculation here, we can approximate it by g at mu x with an additional term, g double prime mu x over 2 times sigma x squared. Okay, so you see only mu x and sigma squared are involved with those, and with the knowledge of the g function, if we can take its second derivative, we can approximate the expectation. So this opens a way to approximate the expectation of a transform random variable if you only know the original random variable's mean and variance, but not its distribution. Okay. Okay, so this is the mean part about y. So let me just give you some high-level intuition about what this actually means. Yes, we ignore n greater than, I wouldn't say n greater than 3, I would say the third order term. Yeah, we ignore those terms because you know, if you are familiar with Taylor expansion, you would know that the more term you keep, the more accurate the approximation is. But the first two terms, the first derivative and second derivative, are more important than later terms in terms of approximation. Why was it possible to take out the mean directly without expectation for the second term? Taking out the mean directly without expectation. Are you talking about this?
Yeah. So like from the first step to the second step, you said because
You mean from, because we said anything involving, so if a term has no random variable involved, it is a constant, and we can always take a constant out of expectation.
Okay, that makes sense. Thank you.
Yeah. So basically, just those are just some simple facts I can say here. So let's say that C is a constant, okay? And X is a random variable. Okay, so with those, then important fact is that if you take the expectation of C times X, it's equal to C times expectation of X. Okay, and if you take expectation of X plus C, it's equal to the expectation of X plus C. And finally, the most important fact, and many people make mistake, is that if you take the variance of C times X, when you get a C out, C needs to be squared. So it becomes C squared times the variance of X. Okay, so these are the facts we will use frequently. And finally, if you just take the variance of X plus C, so that means you shift X by a constant C, the shift will not affect the variance, so it will stay as the variance of X. So I will say that these are the facts we would be used a lot in this class. Okay. So coming back to the result here. So basically you see that the first term is very intuitive, right? We just put the mean of X inside G. And this is a correction term. And in some cases, when G is linear, we don't need a correction. So let's see some special cases. Let's say that G of X is equal to AX plus B. Okay, so it's a linear transformation. So in this case, we can clearly see that G double prime X is 0 anyway, right? So I would say small x. Okay, G double prime small x 0 for any small x in R. So therefore, in this case, then expectation of G of X is just equal to G
of X.
mu X.
G.
Hello.
Mu X.
Okay, I don't think this is a question. Okay, so in this case, you can just swap G and the mean, or basically we can write as G at expectation of X. So you swap the expectation and the G function when it's linear. And this is exactly corresponding to what we wrote here, right? So this is just using the result because expectation of AX plus B, no, is equal to A times expectation of X plus B, right? And then this is exactly G at E of X. So what we derive here is not really contradicting with the special case. So it confirms the special case. Okay, but when G is not linear, especially when the second derivative is not 0, which means that the function has some curvature, right, from calculus, then you need this correction term. So let me just tell you, this is something in my combined lecture notes, but basically it has been posted to CStudy homepage. So that's the place where everybody who wants to preview lectures, you can go there and check the combined lecture notes from past years. So let's look at those two cases where I know the G double prime second derivative is negative or positive. So let's say that I just imagine that my X follows a normal distribution. Just make an analogy. Okay, so for this normal distribution, let's say that we have the mean at mu X. Okay, this is the mean X takes. And let's say that the transformation G takes this form. Okay, this is the G function, and I call this Gx, which is basically my Y. So therefore, with this is a G function, okay? So it maps every value here to every value here. That's the function. And this G function, we know this kind of curvature would imply that its G double prime is negative. It has a negative second derivative. So you see this transformation is not linear, but what it actually does is that looking at the shape, then you can tell for X values that are large, okay, when it maps to Y, it will be shrink because this range is getting narrower and narrower. So you'll shrink the large values once you do the map. While for the small values of X, once you do the map, they will not be shrink. So therefore, imagine that the distribution of X is symmetric around Ux. After the map, because the large values will be shrink, the resulting distribution, okay, so let's say that this is mu X, then mapped here, this will be the G mu X, it will be here, okay? So, but around this mu, for the right values here, once you map to them, map to the Y, they will be shrink. So the range will be like this. Okay. And but for these values to the left, it will be shrink less. So they will have a wider spread. So we can imagine something like this to happen. So now you see the distribution of Y, G of X is not symmetric anymore. But if we look at it, this is the right, this is a larger value, this is small value. So you will have a longer tail at the small values. So therefore, you see when I calculate the mean of Y, because of this asymmetry, the longer tail at the smaller values, the mean of Y will be below this mode, right? The mode is G at mu X, but the actual expectation is below the mode. So that's what we have as the expectation of G of X. So in this case, by this illustration, we can tell that in this case, G at mu X will be greater than expectation of G at X. So this is consistent with the fact that we need the second derivative, a negative term, to reduce the G of mu X to be closer to this, right? If you compare it to this approximation, G of mu X plus G double prime mu X over 2 times sigma X squared, right? So this term is now negative. So therefore, you see, this is consistent with the fact that G mu X itself is larger than the expectation. So that's why we add a negative term to make it smaller. So it's closer to expectation of G of X. Okay, so this is just an illustration to demonstrate that nonlinear transformation can change the symmetry of a symmetric distribution, resulting in the discrepancy between the expectation and the mode, even though before the transformation, expectation is just the mode because of its symmetry. Okay, and then you can draw a similar figure when G double prime is positive. Okay, let me just put it here. Just think about it. So still with this X as a symmetric distribution, around mu x. Okay, now I think consider a G like this. This is a G with positive second derivative. Okay, so with this, first you map the mode to the y. Okay, so again, this is G mu x. But then you see, because of this shape, the larger values of x will be stretched, while the smaller values of x, once mapped, will be shrunk. So therefore, you would have the distribution as has a like a narrower spread here, but a wider spread there. So therefore, you see in this case, because of this new asymmetry, it has a longer tail in the larger values after transformation. So the mean will be larger than the mode. So in this case, the mean will be somewhere here, and it will be larger than the mode. So this is also consistent with that here, the correction factor is positive. So it adds to the G of mu x to make the expectation of Gx bigger. So I'm just trying to explain why this nonlinear transformation can change the mean, and the mean is no longer just G of mu x. Okay, of course, going back here, you can see that if we drop this correction term, that means we didn't keep the second term in Taylor expansion, but just this term, okay? Then you can always use G at mu x to approximate expectation of Gx, but that's a very poor approximation. However, if that's your only knowledge, let's say that coming back to the condition, if we only know Ex is mu x, we don't even know the variance, then that's the best you can do, right? So with your only knowledge of mu x, no knowledge about the variance, you cannot go here. You have to stop here. And I'll just add here. So if we only know E of x is mu x, okay, and y equals Gx, only have those two pieces of information, then expectation of y being approximated by G of mu x is the best we can do. It's a poor approximation, but it's the best we can do. But if we know more information about x by knowing its variance, then we can add that second derivative term to have a better approximation. Okay, so this is the approximation of the mean. Now let's go to the approximation of the variance. All right. So still using the Taylor extension right here. So how about the variance of y? So still using this Taylor extension, now you see to take the variance of y, using the facts I just wrote down here, okay? So any constants added to the random variable will not affect the variance. Any constants multiplied to the random variable will be squared after getting it out of the variance. Following that, here, in this expansion, G mu x is a constant, right? This is a constant, this is a shift, and this is a constant, this is a shift. So we can see that variance of y is not affected by the first term. It's a constant, it can be gone. For this, it's actually equal to, constant will get out by squared. G prime at mu x squared, okay, times the variance of x minus mu x. And the future terms. But for future terms, this is already a squared x term. If I go to variance of x squared, I would need higher moments, like x fourth moments, but I don't know. So I will just leave them out and changing this to approximation. So in other words, I only go to this term and drop the remaining terms. Okay, then I will go one more step. You see, with this approximation, again, I will use the property that the variance of x minus a constant doesn't change the variance. So it's g prime mu x squared times variance of x. Okay, and I know variance of x. That's in my knowledge. So it's g prime mu x squared times sigma x squared. Again, this approximation formula for the variance of y is only depending on mu x and sigma x squared, the knowledge we have. All right, so I will just make the final results in a bracket so everybody have it. Okay, maybe just to summarize. The delta method gives these two results. Expectation of g of x is equal to g at mu x plus g double prime at mu x over 2 times sigma x squared. That's for the mean approximation. For the variance approximation, variance of gx can be approximated, I change to approximation, by g prime, the first derivative of g at mu x times sigma x squared. Okay. So do we have questions for those? These are results based on Taylor expansion of g, of the g function. Okay, with that, let's do a quick application of the delta method to a real case. And let's see how we can apply it. Okay, so in this example, let's assume that here we know the actual distribution of x, so we can do the ideal calculation as a comparison. So let's say x follows a uniform distribution on this interval 10 to 20. Okay, so the question is to find the exact and approximate expectation and variance, or expectation sometimes to be called a mean. Mean and expectation are used exchangeably, and variance of y defined as 1 over x. Okay, and compare the exact solutions and approximate solutions. So let's first do the exact calculation by the definition of expectation and variance. So the exact answers would be, let's do the expectation of y, right? By definition, it's expectation of 1 over x. So we know the distribution is uniform from 10 to 20, that's the domain. So we do integration from 10 to 20, 1 over small x, small x can be any value between 10 and 20, times the density. Because it's uniform, the density is just equal to 1 over 20 minus 10 inside this interval. Outside this interval, it's 0, dx. So this is a simple integral because this term involves no x, we get it out. So it's 1 over 10 times the integral from 10 to 20, this, right? And we know the integration of this is log x. So therefore, it's just 1 over 10 log x from 10 to 20. And it's 1 over 10 log 20 minus log 10. And we know this log difference can be equal to log 20 divided by 10. That's equal to log 2. So it's 1 over 10 times log 2. Okay, that's the exact mean for this y. And if we do this, get the numerical value of this, I'll just write it here. It's approximately 0.0693 for this mean. And for the variance, okay, to calculate the exact variance, what I did mostly is I will get a second moment because it's easier to compute. And with the second moment at hand, I subtract the square of the first moment so I can get a variance. So let's do it. So to get a second moment expectation of y squared, okay, so it's basically expectation of 1 over x squared. And then I use the definition of expectation again. 10 to 20, 1 over small x squared times the density. Okay, so I get it out, 1 over 10. And I know the integration of 1 over x squared is minus 1 over x. So this is 1 over 10 minus 1 over x from 20 to 10. Okay, so a quick algebra will tell me this is equal to 1 over 10 negative 1 over 20 minus plus 1 over 10. So together it's 1 over 200. Okay, that's the second moment. And finally, the exact calculation for the variance of y can be done using the formula expectation of y squared minus the square of expectation of y. Okay, so it's just 1 over 200 minus this 1 over 10 times log 2 squared. Yep. Okay. And this is what? Let me see if it's correct. 1 over 10. Yep. So this will give me actually approximately 0.000195. Okay, so these are just the exact answers using the definition. So I'm just trying to do this as a kind of a review of what we expect you to know about calculating expectation and variance, which is something we should have learned from the 108. So I think for standard 108, it should cover those. But if it is something that just happened to be missing in the 108 YouTube, it's good to make a review. I think it's necessary to make a review to catch up on those things. And also, I will post the class I recommended last time. It's actually called the Harvard Stats 110. I'll post that class material to the link as a link to the CCLE so everybody can check it. It has a lot of YouTube recordings, and it also talks about the MGF, moment generating function. So I think it's a good alternative to check. Okay, so let's see, that's the exact answer. How about the approximate answer by delta method? Let's do it. And it's actually much easier to do the calculation because no integration will be involved. Approximate answers by delta method. Okay, so first, expectation of y is approximately by the g function. Okay, let's first do that. G function at mu x plus g double prime mu x over 2 times sigma x squared. And I'm just copying what we have up there, approximated by g prime mu x squared times sigma x squared. So to do the actual calculation, I need mu x, I need sigma x squared, and I need g prime, g double prime. So those needs to be first computed, right? So to supply the information I need for the computation, let's first use the fact that x follows uniform 10 to 20 to calculate those things. So because x follows uniform 10 to 20, I can quickly show that mu x is the average is 15. And sigma x squared, you can do it either by doing integration by definition, or you can check the known variance formula for uniform distribution. So it turns out to be 25/3. That's sigma x squared. And for the g function, gx is 1/x. So g prime x, first derivative, is -1/x squared. And furthermore, g double prime x is 2/x cubed. So I'm just doing differentiation here. With those, put them inside, then we can quickly do the calculation. So then the expectation of y will be approximately g at mu x, so it's 1/15, plus the second derivative is this, right? I use the mu x, so it's 2/15 cube, right? 2/15 cube divided by 2 times 1/2 times sigma x squared, 25/3. Okay. So together, if I do the simplification, this is equal to 0.0691. Okay, so now you compare this value with the exact calculation. Sorry. You can see they're very, very close. And the exact calculation is bigger, right? This approximation is smaller, but still they're very close already. Okay, now the variance. The variance of y is this -1/x squared. I put in 15 square again, times sigma x squared times 25/3. Together, this will be about 0.000165. Okay, so comparing this number to the exact number, we can also see that the approximation is pretty good. At least the number of digits is correct. Okay, so this is just a numerical example to demonstrate how we apply the delta method. Please note that here we can expect exact answers because we know the uniform distribution as the true distribution of x. But in reality, if we don't know it, we just know the mean and the variance, then delta method is the solution we can use to approximate the mean of y and the variance of y, and y is the transformation g of x. Okay, so any questions about this example and the delta method? Okay, so if there are no questions, the final case note I will give you is the one I said before, the bivariate Taylor expansion. So with the bivariate Taylor expansion, we could prove that joint MGF's result, y the moments is equal to the partial derivatives at 0, 0. And also we can use the bivariate Taylor expansion to obtain the bivariate delta method. Okay, so let's quickly do that. Okay, for the bivariate Taylor expansion, let's say that the function g is the function g of x, y, 2 arguments. Okay. And let's say that we want to expand it at constants mu x, mu y. So pretend that this is the mean of some random variable x. This is the mean of some random variable y. So in the expansion gxy, we will first take the center as g at mu x, mu y. Okay, the first term here is the key. It's actually, so when we take the first derivative of a bivariate function, the derivative is called a gradient, which consists of the partial derivatives against x and against y, right? So it becomes a gradient inner product with the difference. So let me just put it here. So basically, this is equal to this thing. So let me think. Yeah, this is equal to this inner product. It's basically x minus mu x, y minus mu y. This vector times the gradient vector, which is partial g partial x at mu x mu y. And the second element is partial g partial y at mu x mu y. Okay, this inner product corresponds to the first term in our Taylor expansion. So if you think about the first univariate Taylor expansion, we just have x minus mu x, right? Times the derivative g prime mu x. That's what we have there. But now we have 2 dimensions. Okay. And another term going to the second order is that we are going to need this. So 1/2 stay there. It will be a square term. So check here. Let me see. Check what we have here. The square term. X minus mu squared times the second derivative. Okay. So here the square will become, we have x minus mu x, y minus mu y transpose here, and it will appear again as x minus mu x, y minus mu y on the right hand side. This is a 2x1 vector. In the middle, it will be a 2x2 matrix. And that's the second derivative we have for a bivariate function. So once you take the second derivative of a bivariate function, that will become a 2x2 matrix called the Hessian matrix. Okay, so that matrix is actually partial square, okay, partial x squared g at mu x mu y. That's the first term. The next one is partial square, partial x, partial y, g mu x mu y. Okay, and this one is partial square, partial y, partial x, g mu x mu y. Finally, partial square, partial y square, g at mu x mu y. Okay, so this is the second derivative of a bivariate function. And now you see, I have this product as a 1x2 vector times a 2x2 matrix times a 2x1 vector. This is a vector. Sorry, I should write it in a vertical form. My bad. So I should write this as x minus mu x, y minus mu y. Yeah. And so 1x2 times 2x2 times 2x1, that will give me a scalar. Okay, so that's the second order term of Taylor expansion. I don't think pushing the page a bit will help because this is the end of the page. Okay, sorry. So this is it. And you will see that, and so for the remaining terms, I'm not going to spell it out for the third order terms, it's getting more complicated, but we'll stop here. So basically, these terms will be the bivariate Taylor expansion. But if you want to expand it, right, just try to write it out, not using the vector form. I'll take a new page of paper. So if we just write it out, it's based on this linear algebra. So it will be G mu x mu y plus this inner product. I will open it first. X minus mu x transpose times partial G partial x mu x mu y. Okay, that's the first term. And also another term in the inner product is y minus mu y transpose, sorry, there's no transpose, drop it. My y minus mu y times partial G partial y mu x mu y. Okay, I'm done with the first order in the Taylor expansion. Now moving to the second order. So it's basically a vector times a matrix times a vector. So I will just write down the result. It will actually be, okay, 1/2, put everything in a bracket, this result as x minus mu x squared times partial square partial x squared G mu x mu y. Okay, that's the first term. Second term plus 2 times x minus mu x times y minus mu y times partial square partial x partial y G mu x mu y. And by the way, so when we do this partial square partial x partial y, it's equal to a partial square partial y partial x. So the order here doesn't matter. And lastly, I'll just write down here, y minus mu y squared times partial square partial y squared G mu x mu y. Okay, so altogether, these are the terms we need for the second order Taylor expansion. Okay, so with this, okay, so now let's see how can we apply this to the bivariate Taylor or bivariate delta method. So what if now the question is, we have a random variable z that's equal to g function applied to two variables, x and y. So z is a function of both x and y, and x, y, and z are both real valued. Okay, so now we have expectation of x equal to mu x, expectation of y equal to mu y. And furthermore, let's say we have a variance of x equals to sigma x squared, variance of y equal to sigma y squared. Okay, and when we have two variables, we need to talk about their covariance. So the covariance of x and y is denoted by sigma xy. So we denote it this way. And just for your information, if x and y are independent, then they have zero covariance. So therefore, sigma xy will be equal to 0 if they're independent. But otherwise, we should keep it here. So with those, right, these are all the information we have. Again, just in the delta method setting, we don't know the exact joint distribution of x and y. We just know those first moments and second moments of the two variables. So how can we derive the bivariate delta method? And the question is, how can we approximate expectation of y? And how can we approximate the variance of y? Well, sorry, expectation of z and the variance of z. Okay, so I think I will stop here and leave this as a take-home exercise. So you can try it yourself. The key is to use this approximation. The approximation we write up there. So this is basically about let me just put the context here. It's g xy can be approximated by this term. So now you apply this to z, right? By changing the lowercase xy to the uppercase xy, and then add expectation, add variance, and follow what we did in the univariate distribution. Try to derive it yourself. And I will come back and give you the answer next time. Okay, so I have to say that this expansion is only good if you are not familiar with linear algebra because it's just expanded, right? It's a scalar form. But if you're comfortable with linear algebra, then this form is much more concise and it can be easily generalized to more than two variables. So for example, we can say, what if the z is a g function of say p variables with the general p as an integer? So in this case, you can generalize that result. Well, you don't have to expand everything because it's getting longer and longer as you have more variables involved. Okay, so I think that's all I want to say for today, and I'll see you on Wednesday. Thank you.